Well, the category of rose curves look one of two ways. And if you can make kind of focus up here, maybe I've drawn too much at one time. They're the form of r is equal to some constant a times cosine of n theta, or r is equal to some constant a times the sine of some constant n theta. And normally what we'll deal with, of course, is when n is an integer, a positive integer that is 2 or bigger. I mean, if n was 1, that would be circle form, wouldn't it? So I've written down two examples. R is equal to 5 times sine of 3 theta, and r is equal to 4 sine of 2 theta. Now, we want to go through some issues in here, and the next page we'll actually do some graphing, but I want these two examples so we can compare. One thing you might say is why they're called rose curves. They look more like propellers. Well, they were defined as rose curves, or named as rose curves, by an Italian mathematician. The name rose curve, actually, in Italian, obviously I don't speak Italian, I think it's Rodogna. Okay, it means rose. I believe this is how you spell it, Rodogna. Okay, that's rose in Italian. And the Italian mathematician, I believe his name was, and forgive me if I'm Guido, I believe, Guido, I don't know, Grande. And he named this in 1720, okay? So that was long before we had planes and propellers, so I guess it looked like a flower to him, and the greatest flower, of course, for him maybe was a rose. That's where the name comes from. Okay, well, there's 2 or 3 things that we need to know about it. Up here, when we're talking about the A value, now usually A is going to be positive. Usually it's going to be positive. But that value defines the length of one of those loops. And each of those loops is called a petal. So this whole thing is called a petal right here. Or in the graph down here, this is a petal. And we can predict something about these petals by looking at the equation. The absolute value of A is the length of petals. Okay, that's the length of a petal. So in our example in this case, the petal length is this 5. Petal length is 5. And so that means if I measure off over here, 1, 2, 3, 4, 5, that length there is the unit, the 5, of course, whatever that angle is. That's out 5 units along that angle. That's our R value. Okay? And yes, that's the R value. Now, here's something else. So not only can we tell the petal length, okay, we can tell that from the equation. Here's what else we can tell. How many petals? The number of petals is also clear by looking at the equation, but at first it may not be. The number of petals. Well, the number of petals is n. That's the number that's multiplying by theta. It's n if n is odd. So you look at this example, the n value is 3. And since 3 is odd, this graph has 3 petals. Now in the case that n is even, if n is even, then the number of petals will be twice that number, twice of n. That's if n is even. So we look at the graph here, our n value is 2. That's the n value. So the number of petals will be 2 times 2, or 4, and you can see that we have 4 petals. Now, these graphs are on different scales. Here the petal length is 4, isn't it? That's the petal length. And so if we were measuring along here, if we were measuring out this direction, okay, and here would be 1, here would be 2, here would be 3, and here would be 4, so it's 4 units out here. I don't know that yeah, okay, there's the idea of 5 units out there. So we can determine the length of a petal by looking at the absolute value of A, the factor in front of the trig function, and we can determine how many petals it has by looking at the factor times theta. And if that factor, that n value is odd, we have that number of petals. If that n value is even, we have twice that number of petals. Now, when we go about graphing it, let's just kind of stop and think of this next idea. In this example that we have here, back to this example, if we know there are 3 petals, okay, if we know there are 3 petals, and we think, well, okay, then in 360 degrees, I'm doing it in degrees because it's easier to think about right now. That would be 3 petals in 360 degrees, so we're going to have a petal of every 120 degrees. So when we find where the first petal is, then we'll know all of these are 120 degrees apart. So let me kind of draw down the angle down the middle of each of these, okay, and of course this one's right here. So from this position to this position is 120 degrees. And from here to here is 120 degrees. And from here to here is 120 degrees. And of course, if we're doing everything in radians for sure, 120 degrees is how many radians? See, we'd have to figure that out. Well, what would it be? I'd have to stop and think about that. It's 260s, so that's 60 degrees and 60 degrees, and 60 degrees is pi over 3, so it's 2 pi over 3, isn't it? So this angle is 2 pi over 3 radians between each of these. So what we would end up doing, I'm making this really messy now, but if we could find out where the middle of this first petal is, see, if we could figure out on what angle this is talking about there, then we would be able to determine where the rest of the petals are. Okay, we can see it here. Well, how would we figure out where that angle is? Well, that's when we would have the biggest R value, wouldn't we? And the biggest R value is going to happen when we have the sign value equal to 1 or negative 1, I suppose. Okay, but when the sign is equal to 1. So the sine of 3 theta needs to be equal to 1, okay? And so that means, when does that happen? Well, that's when when we take the sine of pi over 2, isn't it? See, that's when we have the sine value equal to 1. So the question ends up being is, when is 3 theta going to be equal to pi over 2? Well, it's when theta is equal to divide through or multiply through by 1/3 pi over 6. So this angle right here is pi over 6. And once we understand where that angle is, then we move to the next position by adding to that pi over 6. So the next petal is going to be at theta equal pi over 6 plus that 120 degrees, which we said was 2 pi over 3. Well, we get a common denominator here, okay? Get a common denominator of 6. So we're going to have pi over 6 plus 4 pi over 6, or 5 pi over 6. That's the next position. So the next, we knew it was pi over 3 apart, 2 pi over 3 apart, but this angle that we're talking about now, and I'm getting this all really cluttered up, but the angle from here to this next middle is 5 pi over 6. So this angle right here we're talking about is at the 5 pi over 6 position. And then we can figure out where this next angle is by taking that 5 pi over 6 and adding 2 pi over 3. Okay, so the next one would be at that 5 pi over 6, add another 2. We decided they were 2 pi over 3 apart. And when we do that, we would end up with, what would we do? That would be a 2, 4, it'd be 9 pi over 6. Well, 9 pi over 6, of course, is the same as 3 pi over 2. And that's what we see here. Okay, so we'll do the graphing in a moment, but we get the idea how we're going to put together these graphs. Now, putting together the graphs and actually drawing the way the graphs would be drawn is yet another issue that we'll talk about here before we're finished. Now, let's get back to this curve that has 4 petals. Okay, r is equal to 4 sine 2 theta. Well, if it has 4 petals, then the petals are going to happen at 60-degree intervals, aren't they? At 60-degree intervals. Excuse me, my bad. 360 degrees divided by 4 is 90-degree intervals. So we're going to have a new petal every 90 degrees or every pi over 2, but we have to find out where the first one is. And once we find where the first one is, then the next one is going to be 90 degrees, or, of course, pi over 2 radians beyond. And then the next one's going to be another 90 degrees, and the next one's going to be another 90 degrees. And then another 90 degrees, and we're back where we started with. So again, we need to know where we start. Okay, that is where the first petal is, at what angle. And in this case, we would find out that that angle is actually at pi over 4, 45 degrees or pi over 4. And so we would know that this angle is at pi over 4, this angle is at 3 pi over 4, this angle is at 5 pi over 4, and finally this angle is at 7 pi over 4. We could figure that out and we could draw the graph. Now, well, let's on the next page, let's kind of start afresh. Oh, before I stop here, in both of these examples, the function that we're dealing with, the trig function, was sine function. And with the trig function being sine function, we know we're symmetric about the y-axis. And in those 3 petals, you can see we're symmetric about the y-axis. If we were to fold it on the y-axis, then we would match. And in the second one, we also have r is equal to 4 sine of something. So it would be symmetric about the y-axis, which it is. You'll notice also it's symmetric about the x-axis. And that will come out as we're drawing the graph. What we knew for sure by looking at the equation is it was symmetric about the y-axis. It can be symmetric in more. We were just guaranteed symmetric about the y-axis. Okay. Well, on the next page, I'd like to kind of start fresh and graph one particular one. We'll get started there. Okay, here, let's graph r is equal to 5 cosine of 3 theta. So let's gather some information. Because we're dealing with cosine of theta, we know we're symmetric about the polar axis. About the polar axis, but for simplicity, we're thinking x-axis. Okay? And that's because of the cosine function. Now, our a value, remember that the petal length depends on the a value. Oops. Sorry about that. It's the absolute value of a. And in this case, a is 5, as we had a while ago. So the petal length is 5 units. Well, here's what else we know. The number of petals, I'm having a terrible time writing, depends on n, okay? And if n is odd, then the number is n, okay? Well, in this case, the n value is 3, isn't it? And since that's odd, that means there are 3 petals. Now, if the n was not odd, okay, if the n was even, then we would multiply that n value by 2, and that's the number of petals we would see. We'll look at an example of that in a moment. So we know it has 3 petals. We know each petal is 5 units long, and we know we're symmetric about the x-axis. Those are the things we know so far. So what we need to do is figure out more or less where the first petal starts, okay? And we could do this algebraically. We could say, what causes R to be 5? We could go about doing that. What causes R to be 5? And we would solve some trigonometric equations to deal with that. But I want us to, at the same time, get an idea of how this is drawn. I am assuming that you've had trigonometry or pre-calculus, and you've done some of this by hand before. So we're not doing a great number of details here, but we still need to be reminded of it. Now, I'm thinking, okay, normally we'd start theta to be 0. Okay, so if we let theta be 0, then what would the R value be? Well, we have cosine of 3 times 0, which is still 0. Cosine of 0 is 1, so R would be 5. So that tells us that we count off 5 units along the x-axis, the positive x-axis, and that's going to be where we start a petal then. That's going to be the end of a petal if it's 5 units long. Now, here's the next issue though. If I choose like I've normally done, see if I choose pi over 2 as my next angle, here's the problem. R would be 5 times the cosine of 3 times pi over 2. And so we're actually taking the cosine of 3 pi over 2. That's way ahead of our plan, isn't it? See, that would be way ahead of our plan. So what we really wanted to do is to choose not pi over 2. Let's not do that yet. Okay, let's choose a theta value. So let's choose a theta value so that 3 theta puts us at pi over 2. And that would be when theta is pi over 6. So let's choose a pi over 6 value for theta. That's a little different than what we've done before. Well, when we do that, okay, I'm down here on my scratch paper. When we do that, then our R value is 5 times the cosine of 3 times our angle pi over 6. But 3 times our angle pi over 6 is actually pi over 2. So we actually have 5 times the cosine of pi over 2. But the cosine of pi over 2 is 0, so R is 5 times 0, so our R value is 0. Well, here's what that tells us. We're starting at this point, and when we have the angle pi over 6, that's about like this, okay? When we have that angle, our R value is 0, so we don't ever leave the pole. We're right there. So the way we're drawing this curve is we're moving along, going like this, and we're right to this position. Now, normally, we would next want to take the cosine of pi. See, that's kind of the way we've done this before, isn't it? But we won't take the cosine of pi by choosing theta to be pi. We'll do that by choosing theta to be pi over 3. When theta is pi over 3, 3 times theta is just pi. So in this case, we would actually have R is equal to 5 times the cosine of 3 times pi over 3. That'd be 5 times the cosine of pi. Since the cosine of pi is -1, R is 5 times -1 or -5. So here's what that tells us. If we're at the angle that is pi over 3, which we'll say is roughly along here, our R value is, oops, I didn't draw that too well, I apologize, along here. Our R value is -5, so we go in the other direction 5 units. And that's going to put us right here. Well, so what's going to happen is this curve, this graph, is moving along in this direction. Remember, we started way over here, and we went to here, now we're moving to here. Now, we're going to get back to the pole. You know, we've got to move back to the pole. We're at the end of a petal again. And so the way we're going to get back to the pole is that we're going to move from this position. We can continue plotting points. We're going to move from this position along to here. Now, how did that happen? Well, again, what would be maybe the next angle? Well, in this case, actually, if we choose an angle of pi over 2, then when we take the cosine, it's 3 times pi over 2, which is 3 pi over 2. Cosine of 3 pi over 2 is 0. So we have an r value of 0. That's why we're back at the pole. Okay. Well, let's see. There's another point I want to make here that's not clear yet. But let me tell you what's going to happen next. What we're going to do next is from this pole, we're going to create the next pedal. And we have to know that these pedals are how far apart. Well, there's 3 of them. There's 360 degrees. 360 degrees divided by 3, they're 120 degrees apart. So that means in radians, they're 2 pi over 3 radians apart. Well, we know where this pedal started. 2 pi over 3 would be an angle about like this. So right here is going to be the end of the 5 units out is the end of that other pedal. Now remember, we were stopped at this position. The way this graph is going to continue being drawn is now we're going to move out to the end of this pedal, and then finally we're going to move back. But let's plot some points to figure that out. The next angle that we would really want here, I'll say, is 2 pi over 3. That's the next angle we would want. And then r would be 5 times the cosine of, whoops, maybe I'm ahead of myself. Let me stop and think here. We're going pi over 6, pi over 6. I believe that's correct. 2 pi over 3. Okay. So we would have 3 times 2 pi over 3. I'm sorry, I'm struggling here. Okay, so we have 3 times 2 pi over 3, and so r is going to be equal to 5 times the cosine of actually 2 pi, isn't it? And the cosine of 2 pi is 1, so r is 5. So the angle 2 pi over 3, that's here, okay, that's what we're talking about. We have an r value 5, so that's how we got there. I mean, we've already drawn that, but it's just the illustration of what's going on next. So maybe the next angle that we would want would be pi over 6 more than the 2 pi over 3. So that would actually be 5 pi over 6, I believe. Okay, 5 pi over 6. So here we go at 5 pi over 6. Then we'd end up, here's what would happen, and I'm sorry, we would get an r value of 0. So at 5 pi over 6, that's this angle out here, and we come back and have this r value 0. That's the reason we came along this pedal. But we're not completed yet, are we? So what we need to do next, sorry that I've got this ugly, let's choose an angle of pi. When we choose an angle of pi, our r value is 5 times the cosine of 3 times pi. But 3 times pi, 3 pi, cosine is -1, so we get an r value of -5. So when we're on this angle of pi, we get an r value of -5, which means we go in the opposite direction. We end up right back here, and so we ended up drawing the graph to there. Now, I hope one of these things, what I hope about, is that we actually saw how this graph was drawn. And I don't know that you can see when I draw over it again, but this is actually the process that we went through to draw that graph. Okay. Now, that's different on how the graph is drawn. That's different than finding out where the ends of those curves are. A little bit different. We could have done that more efficiently if you would. Now, what I want you to notice, though, is we drew this whole graph by going from 0 to pi for our angle, okay? So I'm going to make another note here for you to be aware of. That if n is odd, if n is odd, then the graph is created, complete graph is created with theta between 0 and pi. If n is even, then the graph is created with thetas that have to go from 0 to 2 pi. So it takes more thetas to create it, more values of theta, a bigger interval, okay? Well, that's interesting maybe when we start worrying about things in the next section of the book. Now, on the next page, I want to do one more, and where we have multiple petals again, and we'll worry about drawing it and go about doing this just a little bit differently, but we still want to gather the same information. Okay, we're asked to graph r equal 3 cosine 4 theta. Hopefully we recognize, and that's kind of the first thing, is a rose curve. We've got to recognize that. Okay, once we recognize it's a rose curve, we have petal length that we can calculate real quickly. Petal length is the absolute value of A, because A could be negative, but we rarely will deal with that. And the A value is 3 here, so each petal is 3 units long. Now, the next thing we're worried about is the number of petals. And in this case, and remember it depends on n, so n is 4. That's the first thing. N is 4. And it depends, that's the 4 times theta, right? And the next thing it depends on is whether n is even or odd. Remember, if n is odd, then that's the number of petals we have. If n is even, then the number of petals, okay, is not 4. I should have said that's just what n is. The number of petals is 2 times n. And so in this case, it has 8 petals. That's how many petals it has. Now, what else do we know? Oh, it's a cosine function, so it's symmetric about the x-axis, the polar axis. Symmetric about x-axis. Now, let's stop and think about how far apart these petals are going to be while we're doing this. It has a total of 8 petals, okay? A total of 8 petals. Well, how many radians are there in a full revolution? There's 2 pi. So if we take 2 pi and divide by 8, what is that, pi over 4? Each petal is pi over 4 units apart. Well, that's interesting. Now, we could have done that by saying 360 divided by 8, but that's in degrees. That would tell us how many degrees they are apart. Well, let's do this real quickly. Let's see. I'm doing it in my head. We get our calculator, but certainly 4 goes into 8, and it goes into 360. It goes into 360 90 times, and into 8 2 times. Oh, 90 degrees divided by 4, yeah, by 2, that's 45 degrees. Well, yeah, that's pi over 4 radians, isn't it? So each one of the petals is 45 degrees apart. Okay, well, I guess maybe it's about time to set up graphing. So I guess we could also figure out maybe where that first petal is, but let me set up my graphing right now. Okay, we want to graph this. So let me set up our coordinate axis here. And let's see, we're thinking here we have our, let's see if we can find where our first petal is. We have 8 petals. And the way we would the way I would consider finding the first pedal is finding out for the first value of theta for which R is 3, because our pedal length is 3. That would be at the end of the first pedal. But you know, if we were going along and just not analyzing very much at all, we might say, okay, well, let's let theta be 0. And when it is, then we would have cosine of 4 times 0, as we know, which is 0. Cosine of 0, of course, is 1, so we'd have our value of 3. And so we were at this position, and that's the end of a pedal. Now, let's go a little bit further. So that's where we will start, and that's the end of a pedal. And we know our pedals are 45 degrees or pi over 4 units apart. So we could think, okay, along 45 degrees, here's 45 degrees. If we move out 4 units, 3 units, because our pedals are 3 units long, that's the end of another pedal. We go another 45 degrees. Well, now we're at 90 degrees, or pi over 2. We go out 3 units along that direction. Okay, I didn't make it clear here, but that's 3 units. And of course, we'd have 3 units here. There's our 3 units. And 3 units here. There's our 3 units. We go another pi over 4, or another 45 degrees. So we'd be out this direction. Okay, go 3 units out that direction. Now we're back to pi, an angle of pi, another 45 degrees. So we move out 3 units this direction. That puts us here. Another 45 degrees. Well, let's see, that would put us out in this direction. Okay, so we'd put us there at the end of a pedal. Another 45 degrees. Well, we're at the end of a pedal down here, so there's another 3 units this direction. Another 45 degrees, and of course I'm repeating myself over and over, but we would be there. Now there's the ends of all the pedals. The way the pedals are actually drawn, and we could choose theta values. Here we would probably need to choose theta values. You know, we would kind of think about what theta causes 4 theta to be 0, what theta causes 4 theta to be pi over 2, what theta causes 4 theta to be equal to pi, what theta causes 4 theta to be equal to 3 pi over 2, what theta, you know, and so on, because it's the 0, the pi over 2, the theta, the 3 pi over 2 that we have special cosine values of, okay, to 2 pi. And of course, this is theta equals 0. This is theta equal pi over 8. This is theta equal, pi over 4. Theta equal 3 pi over 8. This is theta equal 2 pi over 4, which is pi over 2. So if we choose those theta values, then we're going to be at some particularly important positions. And so, anyway, I'm not particularly interested in going through all of that right now. I'm interested in how we draw this graph, and we already have the ends of these pedals, and we know that we started right here. So the way this graph would actually be drawn is we'd find out that we go back to the origin, and then we would actually come to this pedal out here, and then we'd go back to the origin, and then we'd come along the pedal that is right here, and then we would go back to the origin, and then as we plotted points, this is what we'd be finding out. Then whoops, I goofed. I put that pedal in too long. Actually, from here, we would have gone out to this pedal. Not bad. And then back to the origin, and then down we'd pick up this pedal. And then back to the origin. Then we pick out this pedal that's going to the left. And then back to the origin. Then we pick out this pedal that's up here. Back to the origin. Then we pick up the pedal that's down here. Back to the origin, then we pick up this pedal that I drew a little too early a moment ago, and back to the origin, and then finally we finish the petal that's out here to the right. And that's what it would look like. Now, it's not so clear until we make a table of values, but that would have taken us to go theta from 0 to 2 pi to get all of that done. What we see here just would be getting us started. Let's see where that would take us, so we kind of understand that remember what I said a while ago, that if our n value is even, then it takes theta from 0 to 2 pi to complete the entire graph. So if we actually had a theta of pi over 8, which is right along here, okay, if we would have had that theta value, then we would be taking the cosine of pi over 2, which is 0, so we'd get an r of 0. So that's how we went from here to here. And then we'd let theta be pi over 4, but then we'd have the cosine of pi, and the cosine of pi is -1, so our r value would be -3. So when we were at pi over 4, which is this angle, we would actually go the opposite direction, -3, and that's why we ended up here. That's why we ended up here. It went like this. And then, of course, we'd have 3 pi over 8. Well, 4 times 3 pi over 8 is 3 pi over 2. And the cosine of 3 pi over 2, of course, is 0, so we're back to our value is 0. That's why we ended up back at the origin. And then we let theta be pi over 2, but 4 times pi over 2 is 2 pi. And so then we have r is equal to 3 times 1, we're back to 3. And that's how we ended up clear back up to this position. And so we really have just done a few of the loops there, and we've got to let theta go all the way up to 2 pi before we get through all of those petals. But at least we've drawn the graph, and right now that's what we were mostly interested in. Well, I want to finish this section with one last type of curve that we run into occasionally, and it's a type of spiral. And I want to look at the simplest type of spiral. That's called a spiral of Archimedes. We'll do that on the next page, and then we'll be finished with this section on polar graphs. I said spirals, and the types of spirals, there are many types of spirals, but we're interested in one that's called the spiral of Archimedes. And it's of the form r is equal to some constant times theta. In the first example, just r is equal to theta, and that's what I'm going to start with, and probably that's all I'm going to be concerned about here. But it's called a spiral because every time theta increases, then we get farther from the pole. Our r value is farther from the pole. And remember, theta is an angle measured in radians. So let's draw a coordinate axis so we can get started with actually graphing one. I've at least got something written down here, and we want to graph, in this case, r is equal to theta. So we just create a solutions table, okay, of polar points, and so we might start out, of course, theta being equal to 0. Well, then, of course, r is 0, and so that means we're at the pole. The r is 0, we're at the pole. And suppose we chose theta to be pi over 4 as an example. Okay, we'll choose theta to be pi over 4. Well, then r is pi over 4, but of course, we need to think more in terms, that's what r value is, but pi, we'll just say, is roughly 3, just so we can get something to work with. And so we're talking about roughly 3/4 is our r value. And of course, that's a distance from the pole. So if we're talking about an angle of pi over 4, and let's say, let's say, I'm just trying to think out loud here. Let's say this is 2 units, this is 4 units, this is 6 units, this is 8 units, 2, 4, 6, 8. -2, we could think, okay, but I'm going to go 2, 4, 6, and of course negative. You get the idea. So along the angle pi over 4, we go 3/4 of a unit, and so that means we're about right here. Now, if we choose theta to be equal to pi over 2, then r is also pi over 2, but pi being about 3.14, that's roughly 3 halves, which means it's roughly 1.5. So now we're about at this position, okay? Now let's let, I'm going to kind of increase the idea here. Let's let theta be pi. Well, if theta is pi, then that's rough, again, our r is pi, and that's roughly 3.14. So that means we're about at this point. And here's what's happened. Well, let me get a few more points. Let's let theta be 3 pi over 2. 3 pi over 2. Well, if theta is 3 pi over 2, of course, that's what r is also. And, you know, in round numbers, that's what r is as well. In round numbers, since pi is about 3, roughly, then this is about 9 over 2. About 9 over 2, which, of course, would be 4.5, wouldn't it? So here's 2, here's 4, 4.5 would be about here. Now, when theta is 2 pi, then r is also 2 pi, and that's about 6.28, really. It's a little more than 6. And so now we're at about this position. So far, here's what's happened. We started at the pole, and we hit this point, then we hit this point, and we hit this point. Now we're hitting this point. You see how we're spiraling out. If we continue now for theta being, let's see, what would that be? 1, 2, 3, 4, 5 pi over 2, 5 pi over 2, then that would be a little more than 7.5. Let's say, I'm going to say roughly 8. I'm just trying to get us to get something. Well, 5 pi over 2 is back to the vertical angle, and we're roughly 8, so we're roughly at that point. So now we're spiraling, and that's what's going to happen. It's going to keep getting farther and farther out and create a spiral of this type as theta gets larger and larger and larger. We're assuming theta is greater than or equal to 0 here. Okay, that's what we're making the assumption of. So that's why it's called a spiral, obviously. And if we had some other constant besides 1, then that would just make the spiral open up more quickly. Or I guess if a was a small number, absolute value of a was a number like 1/2, then that would make the spiral compress or condense. The pieces would be closer together. Well, that's all I have. I know this has been some time going through all of this, but I want you to be familiar with these graphs because we will be using them in the next sections to be able to do some real calculus. So that's all for now.